Welcome, and let's talk about the activation energy and the role that it plays in chemical reactions, and then we'll relate both of those things to enzymes. So the standard that goes along with this is that I can interpret charts and graphs showing the role of activation energy and function of an enzyme in a chemical reaction. So there's a lot in this standard. First of all, it's talking about charts and graphs, which you guys are pretty good at. But in order to understand the charts and graphs showing these things, you need to know a little bit about a chemical reaction, the activation energy involved in a chemical reaction, and then what an enzyme is. So that's what we'll cover today. First of all, energy is important to all living things. Everything that is considered alive uses energy and has to take into account its energy needs in order to survive. So if you remember back to middle school, the definition of energy is the ability to do work. There are several types of energy, and I'm just going to briefly put this up. You're not tested on the different types of energy, but I thought it might kind of bring things together for you, give you a big picture. There are 5 major types of energy. Mechanical, that's anything dealing with movement. So if you remember from middle school, things like potential energy, kinetic energy, all of those things deal with movement, so they're mechanical. So friction, generators and motors and things like that all deal with mechanical energy. The gears on a bicycle moving round and round. The other 2 up at the top are thermal. That's heat energy, or the energy that comes from heat. So this has to do with combustion. This is what makes engines run. It's also the energy that's involved in fire, the heat that you feel. I'm going to go over here to electrical. You guys are pretty familiar with electrical energy. It's anything that comes out of the wall socket for you. Also, electrical energy, you guys know electricity is simply the movement of electrons from one atom to another. So these 3 right here, mechanical, thermal, and electrical. In science, these are mainly studied in physics. You can actually take several different kinds of physics classes where you focus on electrical. You can take physics where you focus on mechanical. Most introductory physics classes will focus on mechanical, but then you can get into thermal energy in physics, things like thermodynamics. You can also get into electrical energy in physics, things with like circuit boards and those types of things. So that leaves us, if these are covered in physics, then that leaves us with these 2 down here at the bottom. There's radiant energy, which is light, and there's chemical energy. Chemistry primarily deals with chemical energy, although all the other types of energy are involved. And we, in biology, are going to focus on radiant energy and chemical energy because this is where the energy for life forms begins. There are some creatures, some organisms that can use thermal energy in order to support their lives, but by and large, most living things use either radiant or chemical energy as their energy source. Radiant energy is obviously light energy, and when talking about living organisms here, we're talking about plants and other photosynthetic organisms that take that light to manufacture sugars and other biomolecules. So as people, none of these other 4 will work for us. We can't plug ourselves into a light socket. You can't move us around enough to give us energy. Obviously, fire isn't a good idea. And we can't just soak up the rays and that be our energy source, which leaves us with chemical. Chemical energy are the energy that are in bonds, and those bonds are made and broken during chemical reactions. So I hope you see that chemical reactions are vitally important to our survival because it's all wrapped up in the energy that we need to survive. So quick refresher, you should know the parts of a chemical reaction. You have your reactants on the left side of the equation. So here we've got 2 hydrogens and 2 oxygens, and it ends up with our products, what you get out of the equation at the very end. So hopefully you've seen this before. If not, take a minute and Google some stuff on basic chemical reactions. Alright, so a basic chemical reaction is when one or more substances are changed to produce one or more different substances. You studied this in middle school, so hopefully that's not too much trouble for you. Also, there's something to realize here, and that energy is always involved in chemical reactions. Energy is always released or it's absorbed. And we're not talking, and an example of energy being released is kind of like lighting a stick of dynamite. Boom, you get a lot of energy out of it. An example of energy being absorbed, if you've ever used or heard of those instant cold packs that sports trainers may carry around, but it's like a little instant ice pack, and you break it or shake it up and it immediately gets cold. What's happening there is as you break it or shake that little bag up, you mix the chemicals that are inside, and they absorb energy. In fact, they absorb thermal energy. So they're pulling the heat out of your arm or your knee, whatever you're applying it to, and pulling the heat out helps reduce swelling and slows down some of those swelling processes. So the energy is being absorbed into the cold pack. But in both instances, well, hang on, we'll get there. So in both of those instances, first, in order to get the dynamite to release a ton of energy, what did we have to do? We had to light it. In order to get the cold pack to absorb that heat energy off of your skin, we had to shake it up and break it. So every chemical reaction requires a little bit of activation energy to get started. For living things, how much energy is this? And one of the interesting things about organisms, especially mammals and large organisms, is that if you totaled up all the amount of energy needed to start all the reactions, the hundreds and thousands of chemical reactions that are running in your body right now, we actually wouldn't be able to survive. Even if we did nothing at all but stuffed our faces with food, we would not be able to overcome the amount of activation energy needed and run all of those processes. So, needless to say, it's lots and lots and lots. So how do we overcome this? How are we actually surviving if we can't even manage to consume enough to overcome the activation energy needed to run our chemical reactions? And the answer is a catalyst. And it's important to know that an enzyme is a type of catalyst. And the definition of a catalyst, and therefore an enzyme, is it's a chemical substance that reduces the activation energy needed for a reaction. Well, I mentioned that there were thousands and thousands of different chemical reactions going on inside your body. And my question then is there one enzyme for every chemical reaction? Or is there lots of different kinds of enzymes that all perform specific chemical reactions? So is it all for one and one for all? And the answer to that is no. For every kind of chemical reaction in your body, there is a unique enzyme. And in some cases, there's more than one. There's about 12, I believe, or 13 different enzymes that all play a part in your making a copy of your DNA and helping your DNA express itself. So even for one process, such as copying the DNA, there are lots of enzymes involved. So back to our standard. One of the things that you're required to do is interpret a chart. So here's a chart. It's kind of a graph. And on the left-hand side here, we have our energy. Below this line, energy is released. Above this line, energy is used. Here's our reaction. We're going to have our reactants A and B, and they're going to make our product AB. The line across here is time, so the start of the reaction and the end of the reaction. The red line indicates the reaction without an enzyme. So there it goes. It has to use a lot of energy. It comes all the way up here for that reaction to even start, which would be about right here. The reaction starts, and we get our products. If you add an enzyme, our activation energy is much lower. We use much less energy to get this reaction started, and there it goes. In looking at this graph, can you identify another consequence of not using as much energy? If it doesn't take us as long to build up to this amount of energy as it does this amount of energy, looking at our time series here, what's another consequence? I hope you notice that the reaction time speeds up. So the reaction time is finished, we get our product, AB, at about this time right here, with an enzyme. Without an enzyme, it takes about this long, so we actually get a decrease in the amount of time it takes for that chemical reaction to occur. And that's important as well. So the two main benefits of an enzyme: number one, and most importantly, they lower activation energy. Number two, they also speed up chemical reactions and enable them to happen faster. Now, as we go through Chapter 3, we'll talk more about enzymes and exactly how they work. We'll even build some models of them so that you can see how they reduce activation energy and how they speed up chemical reactions. Be sure that you can summarize the parts of a chemical reaction and explain the role of enzymes in a chemical reaction.